This is how intelligence is made. A new kind of factory. Generator of tokens. The building blocks of AI. Tokens have opened a new frontier, turning data into knowledge and drawing on all we have learned. Tokens are harnessing a new wave of clean energy. And unlocking the secrets of the stars. In virtual worlds, they help robots learn. And in the physical world, perfect. Forging new paths. And clearing the way for a bountiful harvest. In the moments that matter, tokens are already there. And in the miles between, they never stop. They work where human hands cannot. So we may all breathe easier. And the smallest hearts beat stronger. Tokens are helping us break new ground. On a scale never attempted, to empower the world. So we can reach
Star Cloud 1, separation confirmed.
well beyond it. Together, we take the next great leap into a bright new future built for all mankind. And here is where it all begins.
Good morning. My name is Yogesh Agrawal, and I'm a vice president in the enterprise business at NVIDIA. The video that you just watched is our attempt to show you advancements in AI. I'm going to cover in this talk 3 things. The first is the state of AI and NVIDIA's platform. I'm going to then talk about how this platform and AI is transforming industries. And then finally, I'm going to talk about the importance of AI factories and why this is so critical to this transformation. So let me start with the state of AI. Mr. Pai already helped me quite a bit by talking about the 5-layer cake. Most of us think of AI at the level of models. Jensen, earlier this year at Davos, he actually introduced this concept from an NVIDIA lens that AI is actually a 5-layer cake. AI depends on 5 layers. And the 5 layers are energy, chips, infrastructure, models, and applications. Each of these layers need to scale together. And each of these layers compounds the next layer up. Energy powers chips, chips powers infrastructure, infrastructure then runs models, and models are the ones that enable applications. If any of these layers were to stall, the whole system would stall. And at NVIDIA, our focus is to enable all these 5 layers of AI. So for example, the bottom 3 layers that you see here, they constitute what we call the AI factory. Now in these 3 layers, of course, one of our big focus is to supply chips to the world. But the world is also constrained on data center power and capacity. So that's also something that we are heavily focused on. On the model layer, of course, there is a shift happening towards open source models that I will talk about. And then at the application layer, the shift is towards agentic AI, where a model and a harness now has the ability to reason, they can use tools, and they can execute tasks. And the way we address this is with a full stack accelerated computing platform. I know many of you in the audience probably think of NVIDIA as the GPU computing company. That is not incorrect, but it's only partially correct. We are actually a full stack accelerated computing platform. What do I mean by that? At the bottom layer of this platform, at the hardware layer, we don't just build a GPU. We build 7 different chips, CPU, GPU, networking chips, and so on. And we do what's called extreme co-design, where we design them all in parallel together with the goal of giving you the highest throughput of tokens in the budget envelope or in the power envelope that you have. Now, on top of this hardware layer, we can host multiple domains, not just AI. We can host high-performance computing, we can host AI, we can host visual computing, we can host gaming, and all of them run on the same architecture. So at the next layer, at the second layer, what we give you is the software suite that you need for the development purposes for each of these domains. But we don't stop there. We go one level up to what we call application frameworks, where we get very, very close to workloads and use cases. So for example, we have a framework called Metropolis, which is for computer vision workload. We have a framework called ISAC, which is for robotics. We have a framework called Drive, which is for self-driving vehicles, and so on. And so this entire thing is our platform. What you should also know is that at our roots, we are a platform company. We are not a solution provider. We rely on our ecosystem of developers to build on this platform and then go solve things for industries. There was quite a bit of talk about open source. You should know that NVIDIA is a leading contributor to open model ecosystem. Building a frontier model capability takes like billions of dollars of investment. There are many AI natives who have done that investment, but their models are closed. China, of course, has open model stacks. Now, if you think about it from the perspective of enterprises, what they want to do is they want to start with an open model and then domain adapt it with their proprietary data. But to do so, they want to have a viable, sustainable path to open models. That is what NVIDIA is committed to enabling for those enterprises in the world. We have launched many, many different open models. So we have Nemotron for agentic AI. We launched Cosmos for physical AI. We launched Groot for robotics. We launched Earth-2 for climate modeling. We launched BioNemo for healthcare. We launched Alpamayo, which is for self-driving vehicles, and so on. This is a huge part of our strategy, and we're very committed to enabling this. So the second part that I now want to cover is with this platform, with this state of AI, how are industries getting transformed? I'm going to share examples of 3 industries with you. One is automotive, second is healthcare, and third is financial services. There are many, many other industries, but I just don't have the time to get into it today. So in automotive, there are 3 areas where we operate in: autonomous vehicles, agentic AI, and industrial AI. But let me cover autonomous vehicles with you in a lot more detail. A few years ago, it was all about AV 1.0. In AV 1.0, what you would do is you would use 20 to 50 different DNNs for mapping, planning, sensing applications. And in AV 1.0, your focus was on detection, detecting pedestrians, detecting lanes, detecting vehicles, and so on. Then came AV 2.0, and in AV 2.0, you took multiple of these DNNs into one world model. Instead of using images for labeling, you use video clips. You use transformer-based architectures, which were computationally more complex. And you went from detection to prediction, highly effective, but still not explainable. Now we are in AV 3.0, where AI has the ability to reason. So a vehicle, if it says a pedestrian who is about to get off the curb, it can reason through what it should do. And a model that we launched called Alpamayo, it can actually go through a chain of thought reasoning, where it can look at the feed from video camera and the input from other passengers and articulate why it's doing what it's doing. So explainable AI is what AV 3.0 is about. And this is the kind of transformation that we are enabling in automotive. In healthcare, we are operating in three segments. Uh, there is medical instruments, there is digital biology, and there is digital health. Medical instruments is about a $250 billion industry. And NVIDIA's technology is present in over 400 instruments, from surgical instruments, imaging instruments, pathology, to genomic sequencers, and so on. With AI, what we are able to do is we can now diagnose diseases months in advance relative to what a human physician can do. In the area of digital biology, the challenge is it takes more than 10 years, over $2 billion to bring a drug to market. The reason for that is the likelihood of failure is very, very high. But AI can help. With AI, the first thing that you can do is you can understand the root cause of the disease and figure out where to intervene, what enzyme or protein to go work with. The second thing that you can do is you can pour over chemistry and come up with a drug which has the relevant characteristics that you need. And finally, you can run more smarter clinical trials so you can get the drug to market faster. So that's what the transformation in digital biology is happening. We actually announced a co-innovation lab with Lilly to go drive this transformation. And in digital health, now you have the ability to bring the entire medical literature, clinical trials, patient records, and it's at the hands of the physician so that they can deliver better care. Open Evidence is one such platform, which is being used by over 50% of US physicians. Abridge is a platform that is used for transcription of a dialogue that takes place between the doctor and the patient. And then financial services, I'll just explain it from three segments to you: banking, trading, and payments. In banking, banks have generally run on data for many, many decades now, but the future bank is going to run on intelligence. What does that mean? It means that for any area of the bank, you want to be able to start with an open model and train it with the proprietary data that you have. So you have an intelligence layer that lives and breathes your business. This is the shift that we are seeing take place across the banking landscape. In trading, what we are seeing is that trading firms are using AI to drive outsized returns for themselves. In these firms, a quant researcher used to do feature engineering, but that is now being augmented by deep learning. And so they want to be able to extract signals out of the market, and for them to use deep learning to do that, they're deploying AI trading factories. And in the world of payments, the biggest use case is fraud detection. In India, it's a big one. There is about $43 billion that is lost to fraud annually. And the shift that we are seeing is an emergence of what's called transaction foundation models, which can give you a lot more context and allow you to detect fraud more accurately. So just a sneak peek into various industries. I also want to share an example of NVIDIA and how we are transforming ourselves with AI. The first thing that you should know is there is, of course, closed models. We will use closed models wherever we can use them: Cursor, Claude, and so on. But there is something that is core to what we do. We build semiconductors. Building a semiconductor requires thousands of engineers, multiple teams, specialized methodologies. Our latest chips can have over 200 billion transistors. So to do that, we cannot just use a closed model. We took an open model and trained it with billions of tokens of our GPU architecture. And the result was something called Chip Nemo. And what it can do is junior engineers can go to it, ask questions, saving senior engineers time. It can summarize bugs. It can generate code in specialized languages like Tcl and Verilog and so on. We do use AI for supply chain planning, which is so critical to our business. So these are areas where open models is the basis of what we do. The reason I'm sharing this with you is so you have a framework to think about open versus closed models. With that, let me shift gear to AI factories. So to drive this transformation, companies, nations around the world are building AI factories. The way you think about a factory is you feed raw materials into a factory and you get finished goods on the other end. In an AI factory, what you feed is energy and data, and what you get is digital tokens on the other side. You can think of an AI factory as a highly purpose-built system, highly optimized across compute, networking, storage, software, so that it can process data, it can refine them into models, and it can produce digital tokens at very, very high scale and efficiency. Now, why do you build a factory? A company builds a factory to make money. The same is true with an AI factory. You build an AI factory to make money, and so the more efficiently you can generate tokens from this factory, the more money you can make. I want to give you a framework to think about it with this graph on the right side. Think of this blue area of the graph as a factory that is not very well optimized. And think about the one with the green area is a factory that is highly optimized. There are 4 factors to think about. First of all, how quickly can you deploy the AI factory? The sooner you can deploy, the more money you can make. Second is how resilient is the AI factory? If the interrupts are very high, your throughput will get reduced. Third is, what is your throughput of the AI factory? Not just in the budget that you have, but in the power envelope that you have. And then finally, what is the useful life of that AI factory? So at NVIDIA, what we have done is we have built a reference architecture which is based on our experience of running very large AI factories on our own or running factories for our customers. And so the advantage of that reference architecture is, first of all, we can get an AI factory going really, really fast. The time to first token, the fastest we have done is 19 days for one of Elon Musk's companies. So that increases your revenue. The second thing is, because it's a reference architecture that is well tested, it will be more resilient. Your mean time between interrupts is going to go down, which will improve this part of the revenue. And then finally, also rather the third point is that because we do extreme co-design across 6-7 different chips in parallel, our focus in doing so is to give you more throughput per watt. And so within the same power envelope, we can give you a lot more throughput. So that increases your revenue. And then the useful life, this factory is built on CUDA, which is our main access layer, and there is a rich ecosystem around it. If you look at the evolution of AI, we have gone from CNNs to transformers to mixture of expert models to agentic AI and so on. We have withstand all of these changes with our architecture. Why? Because the architecture is flexible, it's built on CUDA, their ecosystem around is rich. Our A100 GPUs are still very much in demand. So that increases the useful life of an AI factory. And so this is conceptually how you should think about an AI factory. It's directly correlated to revenue. That's why in the slide I say AI factory equals revenue. With that, let me actually play a video where Jensen personally explains how we are building one of our latest racks. So our current GPUs are Blackwell, the next one is Vera Rubin, and Jensen is going to explain how all the technologies come together in a Vera Rubin rack. Let's enjoy.
Vera Rubin arrives just in time for the next frontier of AI. This is the story of how we built it. The architecture, a system of 6 chips, engineered to work as one, born from extreme co-design. It begins with Vera, a custom-designed CPU, double the performance of the previous generation, and the Rubin GPU. Vera and Rubin are co-designed from the start to bidirectionally and coherently share data faster and with lower latency. Then, 17,000 components come together on a Vera Rubin compute board. High-speed robots place components with micron precision before the Vera CPU and 2 Rubin GPUs complete the assembly. Capable of delivering 100 petaflops of AI, 5 times that of its predecessor. AI needs data, fast. Connect X9 delivers 1.6 terabits per second of scale-out bandwidth to each GPU. Bluefield 4 DPU offloads storage and security, so compute stays fully focused on AI. The Vera Rubin compute tray, completely redesigned with no cables, hoses, or fans. Featuring a Bluefield 4 DPU, 8 Connect X9 NICs, 2 Vera CPUs, and 4 Rubin GPUs. The compute building block of the Vera Rubin AI supercomputer. Next, the 6th generation NVLink switch. Moving more data than the global internet, connecting 18 compute nodes, scaling up to 72 Rubin GPUs, operating as one. Then, Spectrum X Ethernet photonics. The world's first Ethernet switch with 512 lanes and 200 gigabit capable co-packaged optics scale out thousands of racks into an AI factory. 15,000 engineer years since design began, the first Vera Rubin MVL72 rack comes online. 6 breakthrough chips, 18 compute trays, 9 NVLink switch trays, 220 trillion transistors, weighing nearly 2 tons. One giant leap to the next frontier of AI. Rubin is here.
So our current AI factories, they are built on Blackwell. Vera Rubin starts shipping in the second half of this year, so tomorrow's AI factories will all be built in this great architecture. But the way you should think about it is, when we release a new GPU, our focus always is on reducing the cost per token, increasing the throughput per watt, the throughput in your budget envelope, and so on. So when we went from Hopper to Blackwell, we reduced the cost per token by 1/10. When we go from Blackwell to Vera Rubin, we're going to reduce the cost per token by another 1/10. That is the kind of transformation and leaps that we are driving in AI. And so while I explained it from the perspective of cost per token, it applies to throughput. The throughput is 10x when you go from Blackwell to Vera Rubin. With that, let me summarize for you. The first point that I want you to take away is that the AI revolution is accelerating. Let me explain it from different angles. One, there are multiple scaling laws that are simultaneously in effect. Pre-training scaling law, post-training scaling law, inference time scaling law, agentic time scaling law, they are simultaneously in action. We have gone from the world of perception-based AI to generative AI to agentic AI to now physical AI. That's happening as we speak. If you look at the kind of computational need that is happening, compared to 2023, the computational need is about 10,000 times more now than what it was earlier. And so to solve all of this, the focus at NVIDIA is we are trying to address this across all 5 layers of the stack that I just talked about. If you look at the last 1 decade, we have improved computational capability by over 1 million times or so. At the energy layer, as I mentioned multiple times, our focus is on giving you the highest amount of tokens in the power envelope that you have. But at the same time, we are also very focused on unlocking energy out there because the world is constrained by energy. So whatever we can do to unlock energy is very important to us. At the chip layer, as I explained, our focus is on designing multiple chips together so that we can help you produce tokens more effectively. When you go to the infrastructure layer, there your objective is to create infrastructure to run AI. That can be on-prem, that can be in the cloud. So we work with all the OEMs out there, we work with the public cloud vendors, but we have also been creating this new category called AI clouds so that our highly optimized reference architecture can be available for you to run AI. At the model layer, I explained to you how we are driving the shift towards open source models and so on. And then at the application layer, I explained to you from the perspective of 3 different industries how we are driving that transformation. We are in over 15 plus industries. And then coming to AI factories, my key messages to you is think of AI factories as equal to compute. But any company, any nation who is serious about AI has to invest in AI factory. That AI factory can be on-prem or it can be in the cloud, but you absolutely need an AI factory. And the more efficiently you can run that AI factory, the more revenue you can make for yourself. So with that, I'll conclude. Thank you so much. Have a great conference. Thanks for having me.